I want to share my.
Yes, sir.
Okay. Last day we have done up to this, right? Up to this, right?
Yes, sir. Yes, sir.
Now what we're going to do, we are going to go for the rest of the derivation. We up to linear region. Now I told you yesterday, not yesterday, the day before yesterday, the equation is valid. The equation is valid until when? Until you got this condition. When your VDS is more than or equal to VGS minus VT, that time this equation is not valid, invalid, right? Right, everyone?
Yes, sir.
Okay, wait a second. I'll be needing this because today I'm at university. So you have seen the graph goes like that. Then after some moment, it falls back, right?
Yes,
But
sir.
it was not supposed to be the case. The graph should go like this. That means it should go up, then it should continue. This was supposed to be the case. But you have seen your equation. I made an Excel graph. You have seen that your graph goes like that. That means at that point, your equation become invalid. So what is that point? That point is the point of saturation. Okay. Point of saturation. Saturation means your current will become stable. It will not increase. It will not be increased with the voltage. That is the saturation point. So when the saturation occurs, we have seen that when your VDS is equal to VGS minus VT, that is the starting point of the saturation. That is the starting point of the saturation. That means this point. So when it is equal, this thing occurs. When it is more than that, you will have this line. Okay. So in our linear region, we will put this. We will put this relation into our equation. Okay. How? See, this is the IDS is equal to beta VGS minus VT minus VDS by 2 into VDS. So we will put VDS equal to VGS minus VT. Where? Here. So we know the saturation occurs when VDS is more than equal VGS minus VT, where VGS minus VT is the effective gate voltage for the MOSFET. Now at the saturation region, we know if we put VDS is equal to VGS minus VT, they have given a set, dot set. It means it is the saturation. It is the starting of the saturation. So VDS is equal to VGS minus VT, then we will get the following equation. So here, at the top, you can see here you have what? Wait a minute. Here, at the place of these VDS and this VDS, we will put VGS minus VT. Here as well and here as well. In the both cases, we will put VGS minus VT. Okay. If we put that, this is your equation. Now, IDS is equal to beta VGS minus VT minus VDS set divided by 2 into VDS set. In place of VDS set, we will place VGS minus VT. Here we will place VGS minus VT. What is the equation now? Here, if I take the LCM, of these three, here you have 1, here you have 1, here you have 2. The LCM will be 2. Now, if we do the calculation, the 2 will be multiplied here, 2 will be multiplied here. So 2 VGS minus 2 VT minus this VGS minus become plus VT, right? This is basic algebra. You all know that. Then into VGS minus VT, what happens here? 2 VGS minus VGS become 1 VGS, minus 2 VT plus VT, that become minus VT. Okay.
Yes, sir. It's okay.
So here you have VGS minus divided by 2 into, you have another extra VGS minus VT that is outside of your bracket, that will be there. So if you multiply this, see, VGS minus VT, VGS minus VT, you have 2 VGS minus VT multiplied, right? So they will become square. And you have a 2 at the bottom. Remember, this square is not on the 2. Okay? This square is not on 2. This square is only on VGS minus VT. So that is your equation now. So IDS is equal to beta VGS minus VT whole square divided by 2. That is your equation for saturation region. Now come to the summarization. Okay, come to the summary. Here, if you have the cutoff region, that means when your IDS is equal to 0, that is the equation, straight cut equation. IDS is equal to 0. Or cutoff IDS is equal to 0. Okay, let me take a screenshot so that I can write something here. So if you see the cutoff region, your equation is this, IDS is equal to 0. If you have linear region, your equation is this, IDS is equal to beta VGS minus VT minus VDS by 2 into VDS. If you have saturation region, this will be your equation. IDS is equal to beta VGS minus VT whole square divided by 2, right? All of you? You can understand, right?
Yes, sir. Understand.
Okay. Now, when cutoff will occur, when linear will occur, and when saturation will occur, that is the condition here. Cutoff will occur when your VGS is smaller than VT. When your VGS is smaller than VT, cutoff will occur. Or if VGS is more than VT, but your VDS is equal to 0, that time cutoff will occur. So any of them, if you have any of these, either these or these, okay? Either these or these, if you have any of these, you will have cutoff, your equation is equal to 0. Okay, now next come to the next region, linear region. When you will have linear region, obviously, you cannot have this. So it has to be like this, right? And you cannot have VDS is equal to 0. It should be like that. So it should be more than 0. It should be more than 0, but less than VGS minus VT. So your VGS should be greater than VT. Your VDS should be more than 0, but less than VGS minus VT. Then your saturation region will occur when your VGS is more than VT, but VDS will be more than or equal VGS minus VT. So that is your 3 conditions, 3 region, 3 equations. Okay. So let's do some math. If we do some
Hello,
math,
sir.
you will see. Yeah.
Sir, VI characteristics graph, where is VGS and VT?
VGS
And VT, where is in VI characteristics graph?
oh yes. VI characteristics curve. Let me show you. Here there is no VT. VT is the VT is the what? VT is the characteristics of your MOSFET. When you make MOSFET, the VT is fixed. Okay, the VT for that special MOSFET is fixed. Let's say for our consideration, let's say it is 1 volt. But here is the VGS. If you increase VGS, so your graph will become higher, higher, and higher. So you will have more current. Got my point? Here you have VDS, here IDS, here you have VGS, and VT is constant. Got my point?
Yes, sir.
Okay, let's see and let's make a graph to see. I'm going to the Excel. Okay. Here, this one will be our VDS. This one will be our VGS minus VT. because this is the condition checker. So if we have to check the condition, this will be our condition checker. Now this will be our IDS. Okay. Now VDS will be 0, 1, 2, 3 like that. So we will go up to 10 volt. Let's say, no, not 10 volt. Let's say we will go up to 20 volt. We'll go up to 20 volt. Okay. Now your VGS minus VT. What is your VGS? Okay, no. Let's copy it. Let's paste it here. This will be your IDS. This will be your only VGS. And your VGS will become 0 to no. When your VGS is equal to 0, this will be, let's say this will be 1, 3, and 7, right? Now I want to find out the IDS here. IDS. Okay. So what is the IDS condition? Now look at this. If VGS is equal to 0, obviously it is less than what? It is less than VT. So here, this whole curve, it is in linear region. Right? It is in cutoff region because your VGS is equal to 0, right? So this all will be 0. Why? Because your VDS is equal to 0 here. If VDS is equal to 0, we know this will be our cutoff, right? If VDS is equal to 0, this is cutoff. Cutoff is equal to 0. So that's why we put 0 here. And if VGS is equal to 0, that means this whole line will be 0. But my point, the whole line will be 0 because this is also cutoff. So this line is cutoff because your VDS is equal to 0. You can see VDS is equal to 0, this whole line is cutoff. And your VGS is equal to 0 because it is less than VT. This thing is less than VT, right? 0 means VT is 1. Let's say VT is 1 volt. VT is 1 volt and VGS is equal to 0 volt. So it is obviously less than what? Less than VT. So it is cut off, right? Understood? It is cut off. So whole line is cut off. This one, your VGS is 1 volt, but still it is not. It is what? It is still not greater than VT. It is still not greater than VT. So it will be 0 as well. It should be more than VT. Now here, these segments, that means where your VGS is more than VT, we will have some result. Okay, so let's find out the result. This equation will be what? Will be beta, but let's say beta is equal to 10 into VGS. What is VGS? VGS is equal to 2, right? 2 minus 1, VGS minus VT, minus VDS by 2. Which one is VDS? VDS is equal to A3. That's right, A3 divided by 2 into A3, right? So that is your voltage. Here, if I go there, you will see it increases, then decreases again. So that is the condition. So this is wrong. This is what? This is wrong. We cannot go that. We cannot go there. Why? Because here you can see VGS is equal to 2 volt. Your VT is equal to 1 volt. So VGS minus VT will be what? Will be equal to 1. 2 minus 1 is equal to 1. So here is the only saturation, only linear region. Here you can see. Now from there, you will have to use saturation formula. How to use saturation formula? Saturation formula was beta into VGS minus VT, right? VGS is equal to 2 volt, beta is equal to 1 volt into 2 minus 1, because you have a square, that's a 2 minus 1, 2 minus 1 divided by 2, right? That is, see, your current is not increasing, right? It is fixed because it is in saturation. Now come to here. I will put the same formula, but this time your VGS is equal to 3. So I will put 3 here. So if I go there and you will see, so it was increasing at some, up to some point, then it become decreasing, right? So there we cannot take those values. We have to delete that. Okay. Now come the saturation. In this point, your 2 minus 1 will not be valid because your VGS is equal to 3 is 3. Now, if I go there, you will see it is fixed again. Right? Now come here. It will be 4 because your VGS is equal to 4, VGS minus VT. Okay. You will see it was increasing until some point, then it become decreasing again. So the decreasing values will be gone. We cannot take those. Now come here. Put it here. Here you have to use 4 because your VGS is equal to 4. So 45. So I can understand this value will remain like that. You understand, right?
Yes, sir, understand.
No, I'm going to use 5 here because your VGS is equal to 5. So I put it there. So that becomes 35. Again, you can see it was increasing. Then after some point, it become smaller, right? So we cannot take those values. That is the only point there we can go with the linear equation, linear region equation. After that, what you have to do? You have to use saturation formula, right?
Yes, sir.
What is the saturation formula? Here in this case, we have to use 5 because our VGS is equal to 5.
Yes, sir, 5.
80. So give it line, it is 80. Now for that, next, I'm going to make a graph because you have asked, sir, what is the, how the graph behaves. So here it will be 6. But if I you can see it is increasing. After some point, it will become decreasing. So it is gone. We do not need that. Same equation, I will write it here, but in this case, this will be 6. This will be 6. Last one. This will be 7 because our VGS is equal to 7. Yeah, you can see it is increasing. At that point, it started to decay, right? So we will cut it there. Now we will take this equation. and place it here because our saturation is starting here. Okay, and in this case our VGS will be 7. It will be 7. Done. Now if I continue, drag it here. Okay. These are the values you can see. So you can go on and on, but I think I made my point. So now let's make the graph. So this is our x-axis, and these are all our y. Okay. So at first I will start with this one, these two. I'll go to insert. Then I will scatter. Scatter is not necessary. I will do that. This one. Okay. See, these lines are all what? All at the cutoff, right? Or I can the chart type. I can make it like this. No. This one. You can see all of the points are at the ground. That means it is cut off, right? Now I want to add select data, right click select data. I want to add, oh, by the way, this graph, you have to edit the name. What is the name here? Your VGS was equal to 0, right? Your VGS equal to what? Equal to 0 volt. Got my point? Your VGS was 0 volt. Now I want to add some. Here our VGS will be what? VGS is equal to 1 volt. And your x-axis will be this one, and your y-axis will be this one. Again, they are same. Now I want to add another series name. This time it will be 2 volt. Your x-axis will be this one. Your y-axis will be this one. Now I want to add another one. Your bridges will be 3 volt. Your x-axis will be this one. Your y-axis will be this one. Add another one. This will be 4 volt. This will be 5 volt. Now it is 7 volt. Move chart to a new sheet. The new sheet is here. Why the other graphs are not here? Because of the X scale. So we want to increase the scale for matrices. We will make it maximum value will be, let's say, 200. What are others? Here, see, our y-axis value is not selected. That's why that was the problem. Okay. This will be our VDS. Now it is all right. Now next one is 5. Edit this. I want to select the x axis, this one. and I want to select the y-axis. Now it is all right. 6. I'm going to edit. Okay. Now here is a graph. Can you see this, everyone?
Yes, sir. Yes.
So you can see this one is your VGS is equal to 7. Okay. This one VGS is equal to 6. VGS is equal to 5. VGS is equal to 4. VGS is equal to 3, 2, 1, and 0. Okay. This is your characteristics curve. That means the VI characteristics curve. So if I give you some, what is that? If I give you some parameters, can you draw this graph? What are the parameters I can give you? What are the parameters? Can anyone give me some ideas? What are the different parameters I can give you? Now here, one important parameter is beta, right? You can see beta. Because your VGS is the variable, you can vary it from 0 to 10 or 100, whatever. Okay, your VDS is equal to, VDS is also a variable, you can change it from 0 to 20, 30, 40, whatever you want. But which one is the deciding? Which one is the deciding parameters, different parameters? So one parameter is what? One parameter is beta, because I can change the beta. Here I have used 10, right? Microampere per volt square. That was the beta for this example. But I can give you different values. And another parameter will be VT. Okay. Now remember, here I have used 1 volt, but in your case it might be different. And we have a derivation for VT as well. It will be at the last of this lecture. VT. There you have to use these formulas. VT is equal to a huge formula. You can see VT is a huge formula. You have to use that formula to determine the VT so that you can use in your VI characteristics. Okay. Now remember, your beta, there was an equation as well for a beta. What was that equation? Remember from the previous class? Remember the beta?
Yes, sir.
What? My mu COX W by L, right? What was COX? COX was actually TOX, no, EOX by TOX, right? Epsilon oxide divided by thickness of oxide, right? Remember. So I can give you different parameters. I can give you EOX, I can give you TOX, I can give you W, I can give you L, I can give you mu, a lot of things I can give you. Then I can ask you to draw the characteristics curve as an assignment. Remember, okay? Not now, but after some point, I will give this assignment to you. So I believe you have to practice this at your home, okay? And since you have seen how to do that using Excel, the Excel is a very, very powerful tool for making graphs. You can do it at your home. I want a graph like that. Now, how can you make this graph more beautiful? You can actually do some formatting. You can increase the text size. You can give some major grid line. Then you can give some minor grid line. You can make a graph like, you can make it more subtle. Okay, you can go format axis, you can go up to 20 or 25. Okay, and you can make this graph a little bigger. Okay, you can make them a little bigger if you want. If you want, you can change the chart type. You can change the chart type from that to these if you want. If this thing, if this is the look you are going after, you can use this as well. Okay,
Yes.
everyone.
Yes, sir.
By the way, you can write here IDS, you can write VGS. How to do that? You can go there and go to the layout. You can see the access title. Here you can put VDS. Then you go there. You can write IDS, right? Then you can give a chart title. VI characteristics, right? Of enhancement type NMOS. You can write it like that. Then you can submit this in an in a document. Okay. So here, what I have just shown you, I have used 3 different equations into what? Into this graph making process. What are those equation? Equation was when your VDS was equal to 0, your whole line will be 0, because no matter what, no matter how your VGS changes, since your VDS is equal to 0, your will be 0. Since this line you can see, when your VDS, when your VGS is less than VT or equal to your VT, the current will be 0, right? So this is one equation. This is cutoff equation. Then at the beginning, that means at the first sum points, we have used linear equation region, right?
Yes, sir.
Then at the bottom of the segment, we have used saturation region. Got my point?
Yes.
So this is a math problem. I can give this math problem to you, do some calculation and draw the graphs. Okay.
Okay, sir.
I will give you an example in our next class. Then you can practice on that. Remember, one of these will be on your final assignment. Okay.
Okay. Okay, sir.
So I believe today's class is over, and thing that I wanted to show you today. And did you submit your lab report 1 and lab report 2?
Sir,
Not yet, right?
last person only submit, sir.
Yeah. Okay. Okay. I have seen some of you have submitted already. Okay.
Yes, sir. It's me.
Okay. Okay, Muraz, is that okay, or do you need more class?
Yes,
More
sir.
time?
Yes, sir.
What?
Sir, more time, you say?